Okay, is everyone seeing that?
I'm seeing a black screen here.
Oh, shoot. Okay.
It's supposed to be slides. Oh yeah, now I see it. There's a little delay. I'm from a hotel in Germany, so it's probably a little delay. Okay, I thank you for. Can you hear me okay? Yes, can you hear me?
We can hear you okay. You're a little glitchy. There's a little glitch.
Okay, I'm gonna stop my video just to to conserve bandwidth. Okay, all right. So that's yeah. So I'm gonna say a few words about QFED. Sorry, it has been a crazy. That's seventh talk that I give in 2 weeks because we have a lab review and it's been a little crazy. Okay, so I'm going to give you a very brief overview of QFED, and some of the things that, or what it is, more in the spirit of a workshop, right? So next one, please. Yeah, so kind of overall idea of the overview is nothing that unusual. I think you probably by now heard GFADS is a top-down algorithm, I think with the same spirit. And we do get the emission coefficients by tuning to AOD. I'll say a few words about that. Not too much about, I don't have too many slides about quality assessment, but I'll say there's a few intercomparisons for things that we did early on. And I will end with some sort of evolution, the kind of stuff, what's in the docket right now, what are the things we are working on. QFED has been sort of, I'll say dormant, we've still been using it, from day to day, but development has slowed down a little bit because we all been distracted by other, activities. Okay, next, please. So, as you know, GMAO has a number of near real-time systems from, 5-day forecast to a number of reanalysis in seasonal prediction systems. And there's a full, what we call geotic composition forecast for reactor gas. And all of those systems run with QFED as the biomass burn emissions. We usually have two versions. One is the near real time. It takes the lens products that you can put our hands on. And then there's a more standard product, science quality, that runs in a couple of days in latency. So I never had any intention to do anything with biomass burning, but if we go back to 2010, we'll be supporting more and more airborne campaigns, and we really needed something to drive those forecasts. Up to now, we have been using GFAD for offline, simulations. But again, we needed something, and the quickest thing to put together is to get fire counts into a quick regression to GFAD, and that's sort of QFED was a joke. That's a quick way to have something, in near real time. So basically, that's where it started. And a few years back, I think we're starting to consider make a little evolution using FRP data. I think all the people from Charles and Yoram that come early on, and all the GFAS development, it seemed to us to be something that really, in terms of near real time active fires, right, not burn, and that's the direction that we went in. And a three-step calibration, we basically, in a very nutshell, we have some procedure to grid, FRP, and then we need the emission coefficients per biome. Currently, we are using very simple, for biome. I'll say a few words later in GFAD. And so the way we do right now, all the trace gases, we tune those emission coefficients to sort of be consistent with GFAD, and that was GFAD 2 or 3. I'll have some slides later on. But of course, as you know, GFAD typically do not produce good simulations of Eros optical depth. It's usually about 1/3. So we ended up doing a inverse calculation to match AOD. So, and that's what we do. There's a little disconnect here between the trace gases and the aerosols. And when you use them in the forecast, as of right now, we are persistent emissions. There's no fire model actively running in none of our products. Next. So yeah, it's basically what I said. We have 4 biomes that we are looking to expand. It's the boreal, the tropical fire, the savanna, and the grasslands. Spatial structure comes directly from the FRP, and we do account for obscure pixels. And next slide. Next. Great, thank you. Yeah. So basically, that's the typical grid box, right? So you have several pixels in that grid box. One is, pixels that you can actually see and are water. So those are not going to be burning. You have pixels that are, for some reason my red went into green, but there are pixels that we determined they are burning, and a number of them are the 0 observations, right? So those are very good observations. So basically, we take in that and then of course there are areas in where obscure, there are clouds or the swath, cut you out there. So the idea is we have the final FRP density is a linear combination depending on the area weighted for each one of those FRPs. Of course, the 0 ones, they're not burning 0, the water is 0, and the burning is the FRP that is reported. And the green box mean is a weighted average for the area. And in the end, we need a procedure to deal what's happening with the obscure pixels. So several approaches. One is out of sight, out of mind, right? So you do not see any fires. Let's assume it's not burning, and that's give you a low bias. You can extrapolate, right, and see whatever's in there, what comes from, what you don't see is like what you see, and that's also problematic because you happen to see a little corner with one fire. Extrapolating that, you really, we've done all of those throughout time, and then so we ended up having something, a relatively sequential algorithm for what the density for the obscure pixels, which is basically we have a prior, right, which is usually the biomass burn in that grid box the day before with a dumped persistency model. And then you have also the parts that you actually observe of the grid box. And it's basically there's a scalar common gain here that's parameterized in terms of the area. So you basically, most of the grid box is covered by obscure, pixels. You ended up sort of taking, what was happening the day before. If it's fully observed, then you take, basically the extrapolation method is actually combined according to this. So it's a simple, sequential estimation in our algorithm. So that's basically the gist of it, how we include the observation. So of course, we do need access to the full geolocation of the level 1 pixel. Next. So that's the 4, biomes that we take: tropical forest, extratropical, savanna, and grasslands, and that's the IGPP sort of category that goes into those 4 aggregated, biome. Next. So for trace gases, we do a tuning to QFED for CO, right? So, and once you have emissions for CO, use basically very simple-minded ratios of coefficients to come up with the other species. And that's pretty much the species that we provide. For aerosols, though, we use those emission coefficients, right? What multiplies the FRP. We tune them in such a way to match the aerosol optical depth, right? And I'm not going to go into the details. There's a global. I'm going to show some examples in a sort of regionalized sort of regression that's easy to explain, but actually there's a global cost function. The thing gets minimized, but it's basically 4 constants, right? That you try to minimize to match, the observed AOD, and you restrict that cost function to the regions that are primarily dominated by biomass burning aerosols. Next. So here is Basically, the tracecast is the kind of regression in log space that you do to come up with a CO in terms of GFED. Here's a quick comparison on the right, the difference when we went simplifier counts to FRP, right? It's not enough to have more fires, but we can account for the intensity present in FRP. We ended up having larger emissions for some of the more extreme events. Next. So that was all. Emission tuning is basically, is a very simple sort of Green's function kind of tuning, right? Have 4 constants, each one for each biome. And there's something up for the anthropogenic and stuff that we usually, we do not start using that to tune that globally. And so you decompose the emissions, and the system is quite linear at the end. And we ended up sort of, having a decomposed and also optical depth at 550. And we use our sort of narrow net AOD, which is trained against AeroNet, to come up with those coefficients. And you can do that. We're, actually in reality now we're doing globally, and I will show you next a few examples when you do that sort of for small regions. Next. So that's one of those typical regions people use. That's from a paper by Charles in 2008. Next. Okay, so I'm going to go for a few regions here. You can see the numbers in the map. That's for Africa, and you can see pretty much what you have to do here in the top figure. Black is the observation, right? So that is the observed AOD, and the red one is what we obtained for tuning based on GFED, right? Simple mother GFED, and that's in the blue one is the regression, right? To match the AOD, and you can see pretty much you capture the seasonal cycle. 15 is not that great. Some regions work much better. 16, has a good sort of, you reproduce the seasonal cycle AOD quite nicely. As I said, those are for regions dominated by mass burning. Next. Here's for South America. You can see region number 8, right? The core of the Amazon. It's kind of nails the seasonal cycle of AOD. 10 even is not that bad, although it has a little misses in the back. And 9 is the semi-arid region of the Northeast. Not too many fires in there, but it basically captures quite realistically the AOD diurnal cycle. Next. North America is a little bit problematic. You do get, you can see region 7, you can get the diurnal cycle. Some other regions like 1 in Alaska is a little tricky, but you see there that it does the blue and the red. Climatological really gives you the right thing. And that's the next one is the more problematic Southeast Asia. Some of those really do not work quite well. 32, right? And it does a reasonable job. 33, I cannot get those islands straight, not even going to try. You can see there's a lot of mismatches. That's actually our most sort of challenging region is like we were for compacts in 2019. So that is our most challenging areas to match AOD. Next. So I'm probably not going to go to the next slides. I think we're going to have talks later on people comparing QFED with other emissions. We had done some comparison, and that came from the tech memo, the original tech memo, comparing to GFAS and other ones. Next slide. Maybe you can go quickly over those because I'm not going to go over. I think it's going to be covered that elsewhere. How we compare with the Flambe, and that's an older version of Flambe. Yeah, flammability. Let's keep that. So there's several examples that we use. That's part of our analysis FP forecast system, right? So I had actually other animations for some nature run and things so you can really see the plumes and the time evolution, but. We have really been, it's our workhorse, that's what we use for everything. Next. Okay, S2S, we have been using biomass burning in S2S. What we run right now has climatological biomass burning aerosols from QFED. If you go to the next slide, and then you can see that if you simply prescribe climatological aerosols, and that's the AUD for the climatology, for climatological emissions, upper right, you can see you can get sort of the gist of the seasonal cycle. You cannot get the interannual variability. There's no way. Of course, if you cheat and you run the seasonal system providing the actual fires that happen, right? It's really, cheating, but just for the sake of it, you see that you for that particular region in South America, you do get a lot of interannual variability because they're actually coming from the emissions. So there's no good way. It's different for dust and the more dynamically emissions, but we do need to do something very critical here for if you want to have any skill in predicting the internal variability of biomass burning aerosols. Next. So one of the things that we haven't implemented is to use a very simple parameterization where we do what we do right now. We have the climatological QFED emission, but then you modulate the air quality index, which is basically the ratio between the fire weather index, right, for that particular year divided by the climatology with a power and a coefficient, and you can actually tune that over the years and come up with good point sort of tuning parameters. And what that does in places where this relationship does not work, that coefficient, goes to zero, right? So it just basically revert back to climatology. So it has a do no harm. And I'm cherry picking here. I'm showing you where it works best, which is the maritime, continent, right? You can actually capture the INSO cycle and basically the interannual variability. Places, for example, that has absolutely no skill is the border forest, right? Think about fire weather index was developed for that region, but that does not, and not quite sure exactly what it is. If it is, lighting is basically the triggering mechanism that we are not really, capturing or implementing. So it doesn't. But again, for the tropical, fires, it has, some skill, but we are yet to fully implement that in the S2S. So it's technical glitches along the way. Next. Okay, some features, what we've been working on. As I said, QFED has been sort of in a slow sort of back burner. And we just hired someone, Meng Zhao is one of the courses here, that would be sort of having time to full-time work on the biomass emissions. One is surviving mode is, of course, what we have right now is VIRS for the PM orbit. We're still figuring out what to do for AM orbit. I hope you guys are going to have a good discussion about what to do with estimates from, the Sentinel, and there's some pilot studies at NASA, and at this point, it's probably not right for prime time. So I wish I could actually participate in your discussions. Another one I'm going to probably give a quick example next is the estimation of modified combustion efficiency, right, from satellite based on collaboration with Jun Wang at Iowa. And vertical mass distribution in ways in which we can use the plume rise, not by specified heat flux, by doing inverse calculation from top of the atmosphere thermal anomalies. Not going to talk much about it, but that is on our radar screen. And of course, we need to get our hands with geostationary data, to properly blend with VIRS, which is not an easy task. But okay, next, quick development path. I think I already said most of it. Adopt biome, including peatlands. We're not explicitly dealing with peatland, but we really need to do that. So we're going to have 7 biome, I believe. We're trying to adopt what's in GFED. The MC for modulation of the emission coefficients, right? So you can use that for to have a state-dependent, translation between and seasonal emission anomaly, as I said, and injection height. Okay, let's go next. I'm just going to say, in terms of time, talk about what we're doing with the modified MC. Everybody knows what MC is the ratio can express as the emission factor of CO2 over CO2 plus CO. And basically, people have been parameterizing emission factors in terms of MC, right? So you can have a little, kind of little regression between MC in the emission, factors. It seems to me, after a lot of experimentation, a lot of those regressions give you something very close to 1 minus MC. So for several of the tracers, I think 1 minus MC there's a very sort of practical application because you can actually almost trivially, once you have MC, see that you kind of combine that with the FRP estimation, and most of the QFED algorithm remains the same. But of course, not every tracer satisfy that relationship. As you know, black carbon can be very nonlinear, and there will be a lot of experimentation and to do it. But let's see what we're doing for MC next. That comes from the work done in the University of Iowa, where you have the FRP, right, from the 4-micron channel. You can use the day-night band to have all during the night, the 5 visible light power. If you make the ratio between those two, you get something that's very much, correlated with MC, right? So basically what we estimate is basically the flaming sort of fraction of that fire. And you relate that to MC to a relatively simple expression, right? So that works quite nicely every night. I think it gives something usable, right? At night using the day-night band on vias, which of course we don't have such a band in MODIS. Next. So here's a typical sort of map throughout the day, and that sort of little insert in there to say you can use the 2 vias or NOAA 20 or 2 MEP, and they are rather consistent between the 2 satellites. So you're able to have this global estimation. FILDA is the fire detection project from Iowa. It so happens, if you look at the mod 14, if you're working that data, only has 2 channels, right? The 11 micron, the 4 micron. We actually will need for the algorithm a few more channels. So, it's required just to go back and do the whole fire detection again. But next. So the thing about at night is if you want to do something from MODIS does not have the night band. So what we're doing here is to use machine learning to train what we're obtaining with the night band using exclusively IR channels, right? Thermal IR channels that you can find in MODIS, right? So basically, here is all in vias, but you can actually locate vias in MODIS and develop such a model. And you can see on the right, there is relatively good skill that you can get the same signal relying strictly on the thermal IR channels. Next. And of course, that works overnight. So we expect to extend that to MODIS and go back to the to the beginning of Terra. It's a little harder to do that over the day, so we're still working on it. We haven't really given up, but have reflected radiation. You cannot train a model, a machine learning model overnight to expect work during the day. Actually, doesn't. But there are ways we can probably use the 2 micron channel despite even the saturation. You can still get 95% of the fire. There's other analytic algorithms that can probably be done. So that is still sort of we're figuring out what to do during the day. But at least we hope to have something at night that can go back to the MODIS period. Next. That's all that I prepared for today. Sorry about rushing through it. So QFED runs in near real time. In mode has been what we use all the time. So we just added, vias, and geostationary is, something we like to do. You have data products, near real time, and, standard, and we can use that for all our reanalysis on real time systems. So that's what I had. Any questions?
Thanks so much, Arlindo. Shobha has her hand up.
Sure.
Yeah, thanks. Yeah, thanks. Arlindo, quick question. So we heard from GFED team this morning. So as their product is evolving, do you have to keep up tuning your QFED? As you know, we tune GBEPX, which I'll talk about tomorrow, to QFED. So any updates, and then we know you tune QFED to GFED. So I'm curious.
I think we should do that. I think that's part because we have to retune the AOD, right? And I think we need to go now. Now that we have a dedicated person working on it, we're going to go systematically in redo for QFED 3.0. We're going to do all around retuning. Okay. Yes, so that is the goal. So I have to check GFED team where they are and look at their validation and stuff. But I think it would make all the sense. So I have no intention to, it's just going to leverage the kind of work they have been doing in terms of calibration.
Thanks.
Just a few more minutes if anyone else has more questions. Oh, there's one in the chat now from Ed. Ed says, Arlindo, how does QFED treat black carbon? What sources of systematic variation in BC release are included?
And so right now, we just use all the ratio of emissions between OC and black carbon. There's nothing really special being done right now. And one of the motivations to go into MCE is because now we can actually have the ratio OC to BC not to be a constant, right? Like we have right now, is to be able to use the information on combustion to, to basically have, a different ratio. So right now, not doing anything yet. It's very simplistic.
Okay, thanks. And then there's another question from Feng Jin. Says, nice talk, thanks. A quick question about QFED resolution. Is the quarter degree QFED aggregated from 0.1 degree QFED?
Yeah, so we have, because the way things done, we run the algorithm twice in two separate grids because it's a sort of sequential, right? I talk about this obscure, you have the day before. So we don't simply get one product and aggregate. We rerun the whole thing on a different grid. But I never checked, but it should be relatively, equivalent. We will be we're still going to be putting out the slack lawn kind of products because I think what some people like. But more and more, we will be working directly on our CubeSphere grid. We're going to have one version of the product that goes to, the CubeSphere quasi-eco area, which is, probably would avoid us to do any kind of remapping, interpolation, and especially it's important to keep that for point sources, right? Every time you interpolate, it leaks over and it diffuses the fire, several grid points around. But no, the 2.5 is not a regridding. It is actually something computed independently.
Okay, Shobha?
No, I don't have a question, but I was hoping Feng Jin would actually speak about his experience in some of the issues when you're using multiple sensors and remapping from or aggregating from one grid resolutions to the other. Feng Jin, you want to say anything about that? I will show your slide tomorrow, but in case you want to.
Thank you, Shobha.
Go on.
Yeah. Oh, sorry about that. Yeah, I think Shobha has a slide to show tomorrow to see. When we do the GPEX, we have seen like when we run the same algorithm, like in the quarter degree, or in the 0.1 degree, we have seen like very large differences in the emission mass when we have done that. So that's the reason I asked the question. And then also personally, I did some comparison as we work on the GBACs. So I did some comparison between 0.1 degree QFED and then 0.25 degree. It seems like the emission mass over the same region seems not much each other exactly. So there are some like differences there. So I don't know, have you ever have such kind of a comparisons? Thank you.
No, because so honestly, we've been using the 0.1 degree. This primarily for the nature runs, right? For which, has to be realistic. We haven't really been using, well, actually, we use that for the other one. No, we haven't really compared the products too closely, except for, seems reasonable and do some scatter diagrams and finding the things are like in fires, right? Every time you do a scatter diagram, you don't get anything. There's always noise that pops up, but there's nothing that create alarm to us. But if you have something specific, probably we should take a look at.
Hey, thanks, Orlando. There's 2 more questions in the chat, and then we'll stop after that because the day's almost done. So I'll ask the second one first because it sounds like it's a yes or no question. Ed Heyer says, Orlando, are you distributing CubeSphere gridded products through NASA already, or is that still in the future?
No, it's still in the future. We have that in sort of the development, version that we have, but will be in the future. And it's usually that's on the HTTP side, that you can get directly from us. We haven't been sending that to the DAC. We could at some point, but sometimes just dealing with the metadata issues just because more time that I have. But no, not yet, Ed. That would something that's coming, but we haven't really distributed that. It's just in our development version.
Okay, great. And then the last question is from Carrie Anderson. It says, you propose using FWI in QFED calculations. Could you elaborate a bit more?
Yeah, not in the QFED, but that is for the seasonal projection system, right? So right now we are running with climatological biomass burning. It's a small extension. We have used that parameterization where we try to modulate the climatological one with an index, which is the ratio between fire weather index at the moment over some climatology in the power. But that's not part of QFED. That is something that we can use calculation FWI for our S2S system to bake into some form of internal variability in the emissions, because without that you cannot get the aerosol concentration, right? Internal variability aerosol concentration. Kind of simple-minded. Let's get some thing there that gives you some of that behavior and then evolve.
Okay, thanks so much. And we're just a minute away from when we plan to end. So first of all, thank you to all the speakers for the fantastic presentations. And I'm also amazed that we stuck to time so accurately. And thank you for everyone who asked questions and participated. I just wanted to mention that as you know, this session is being recorded, and eventually we will post for the speakers who filled out the consent form, we'll post the videos on YouTube eventually, a few weeks maybe after the workshop, and we'll send the links around. Tomorrow we will have 3 more presentations on the fire emissions data sets, and then there'll be a break, and then there'll be 3 more presentations on intercomparison studies. The program is online. Oh, I wanted to remind you if you look at the program online at day 3, it will remind you what the discussion questions will be. And we encourage you to keep those in mind. And just want to add that if there are other discussion questions you'd like to include, you could email one of us, and we can try to get that into the discussion breakout rooms. Nancy, Rebecca, Mark, anybody? Did I forget anything before we adjourn?
See everyone tomorrow.
Okay.
Yes, and thanks,
Thank you,
Nancy, for
guys.
stepping in. I had some technical problems. I'm afraid to turn my video back on.
Yeah. Sorry, I won't be attending, not for the lack of interest, because I'm in another workshop, but I look forward to the recordings. I'm really upset that I'm missing this.
Thank you for doing your talk despite that.
Oh, no problem. My pleasure. Okay. Good night.
Okay, thanks everybody. And yeah, anyone who can make it, we hope to see you tomorrow. Okay, take care. Thanks again. Bye for now.
Thanks a lot. Bye-bye.